Welcome everyone to my course Formal Methods for System Verification. In this week we are discussing formal property verification. So, in last two classes we have introduced how basically the formal property verification works and how to write the properties, right. So, if you remember, the process was like this, right. You have the design specification, from there the verification engineer will write the properties. So, this is can be written in LTL, CTL, right, LTL, CTL, or maybe in SVA or PSL also, right, system verilog assertions and all in some specific language. And the design engineer will read the same specification and interpret in his own way, and he will implement. It is in RTL. Let us say this is RTL design, which is in verilog, VHDL or system verilog, right. So, you will get these two things. Now, your objective is to check whether this particular implementation satisfy these properties or not, right. In the last class we discussed mostly on this. So, given a specification, how do you encode those property in LTL, right. So, today we will see mostly this part, which is basically the how this model checker or the property verification engine works, right. So, as I mentioned, so within the model checking, usually the way we check the formal property is called model checking. Okay. So, objective is that you have set of properties, set up and the implementation, and you have to check whether this implementation satisfy these properties or not, right. So, this is the objective. So, internally this model checker has basically two main component. One is the FSM extraction and the model checking algorithm, or model checking engine, right. So, to give you more emphasis here, so you think about I have some implementation, right. Now, to check this property on this implementation, you cannot just check directly on this kind of implementation. What you have to do? You have to identify the state machine or the finite state machine that is happening inside, right. So, you will effectively identify some finite state machine like this, and this is basically FSM state extraction. We will talk about that more. And then what model checking does? It basically try to identify some path here. Let us say this is my start state. It try to identify some path here like this, right. So, some path is going like this. In this path, whether this property holds or not, right. So, this is basically going to happen here. So, there are two parts here. One is most important is the FSM state extraction and the algorithm, right. So, in this course we will mostly focus on this algorithm. How do you implement this LTL or CTL model checking algorithm when you give such property? How do you check in a given FSM, right. So, this is the first part we will do, and then I will talk about more at the end of this class. You will understand more on this, okay. And then finally, the advantage of this model checker is that if it say yes, this particular implementation satisfy this property, it is giving 100% guarantee that in all possible scenarios, all possible input, this property will always hold in this, right. You do not need to run simulation or you have to test, you do not need to do anything. So, it comes with that 100% guarantee, and that is the most important point of this formal way of checking properties in an implementation. But this comes another big advantage if it does not satisfy, okay. So, it will give you some counter example. It will say if your input is this, then after if you do this, then in this state in this particular clock your property will be violated, right. So, that is the biggest advantage of this model checker algorithm. It does not only give you 100% guarantee when it satisfies the property, but when the property fails in the implementation, it actually identifies the bug in your implementation, right. It basically gives an input scenario under which this particular implementation does not satisfy your property, right. So, this is very important, okay. So, we will talk about more in that in subsequent classes. So, what we will go today is basically we try to see this part, right. So, we will basically talk about this FSM extraction given an implementation, how do you extract the FSM, and then we will also talk about briefly about this model checking algorithm, how it basically identify the paths and check the what is the relation between this path versus the property that is given, right. So, it is just an overview class, it is not something that we are going to talk about the entire algorithm today. We have subsequent classes where we will introduce the algorithm more precisely. Today just give you some notion what is happening inside the model checking tool, right. So, to carry on this discussion, we will take the same arbiter example that I am taking for the last two classes, right. So, if you recollect from my previous class, the arbiter is something kind of a manager for some resource, where multiple user can request to use that or access that resource, and based on certain priority, some function, it give access to one of the user, right, at a time. So, that is the arbiter. So, in our example, there are two requests and there are two grant, right. G1 is corresponding to R1 and G2 is corresponding to R2. So, if there are two requests coming at the same time, the arbiter decide which grant he will give, right. And the specification given for this arbiter was this. This we have discussed earlier also. The specification was like, if R1 has the higher priority. So, if whenever R1 come, next 2 cycle you have to give G1 true, right. So, that is the first property, and then you are saying then there is no request, you give by default G2 access in the next cycle, and G1 and G2 are mutually exclusive, that you cannot give access to both user at the same time, because you have one resource, right. So, we have already discussed about the consistency, completeness of this specification, and then we identify these are the 4 property that actually encode correctly that specification. Just to recap, what are the properties? So, the first property says that globally, if R1 is true, X is next. So, next clock G1 should be true, and XX next to next clock G1 is true. It is basically modeling that whenever R1 comes, next 2 cycle G1 should be true, and it is globally hold, it is whenever it happens, right. The next property says that when there is no G1, you can give by default G2 grant, and this is the mutual exclusive, that at a time at least one of them should be 0 globally, the mutual exclusive. And we have also seen that inconsistency in the specification. So, we have added this, that if this R1 is not there for 2 cycle, you make G1 is 0 by default, right. So, this we have discussed in the last class. So, we have this specification, we have this property identified by the verification engineer from this specification. Now, from this same specification, design engineer who write the RTL code, they understand this, and let us say they have implemented this Verilog code corresponding to the arbiter. Just so, this is in Verilog, right. This is Verilog. We do not need to bother about much on Verilog in this course, but just to tell you what is happening here, it is saying that in this arbiter you have 3 inputs, clock, R1 and R2, and your output which is registered, and it has G1 and G2 is the output, and you are saying then every positive edge of the clock you do this. So, you assign G2 by this way and G1 by this way. So, whether this is correct or not, I do not know, but if this particular implementation satisfy all this property, then I will say this implementation is correct. So, that is what I am going to see today, whether this implementation correctly model this particular specification or not. There may be bug in the implementation, and if there is bug in the implementation, then some of the properties should fail in this implementation, right. So, that we will basically will see throughout this class. Okay. So, as I mentioned, the first job is to identify the FSM. So, how do we identify the FSM from this implementation, right. So, that is the first question. So, what is finite state machine? Is basically you think about it has many states, right. You have basically states and there are state transition. So, what happened? What is this state means? It is the current value of your sequential logic or sequential elements. What are the sequential element in your design? The register, which can store which is kind of a memory in your hardware, right, which can store the values. So, this state bit will be all the registers that you have in your design, right, which is G1 and G2. So, your state will be encoded as G1 and G2. So, there are 2 bit. So, there are 4 possible values, that is why I put 4, right. So, you are basically it can have 0 0, 0 1, 1 0 and 1 1. There are 4 possible state your design can be. So, it is means your 0 0 means none of the grant is 0, here it means G1 is 0, G2 is 1, here G1 is 1, G2 is 0 and both are 1, right. So, these are the 4 possible states. And what is happen? If the request will come, if you are in this state, if request come, then I will go to this state. So, what are the request or the level for this transition? It will be the inputs, right, R1 and R2. Clock is basically controlling the sequential behavior. So, this is not something will be considered here, but your case will be R1 and R2 is the state level. So, what is going to happen? If your G1 and G2 is this, if say your R1 and R2 is 0 0, should we stay here, should we go to this state, should we go to this state or should we go to this state, that is what we will identify. Okay. So, let us do this. So, this is my implementation. So, if we write G1 is basically R1 and G2 dash, right, this is the next state is not of R1 and not of G1, not of R1, not of G1, not of R1, not of G1 and R2, right. So, I mentioned that my state variables are G1, G2, right, which is, and then transitions is inputs R1 and R2, right. So, what will happen? You have G1, G2, R1, R2, and then you will say what will be my next state, G1 dash, G2 dash. So, this table we have to construct, right. So, as I mentioned, there are 4 possible states 0 0, 0 1, 1 0 and 1 1. So, I will show some of the things. So, if your current state is 0 0 and your input is 0 0, what is going to happen? If R1 is 0, G1 dash will be 0, right. So, next state G1 dash will be 0, and if R2 is 0, automatically this equation will be 0. So, it will be 0 0. It means, if you are in state 0 0, your input is 0 0, you will remain in this state, right. Similarly, there will be 4 combinations 0 0, 0 1, 0 0, 1 0, 0 0, 1 1. So, if you are in 0 0 and if your R2 is 1 and G1 is 0, R1 is 0 means G1 will be 0 and R2 is 1. So, this is 1, not of R1 is 1 because R1 is 0, G1 is also 0. So, this G2 dash will be 1. So, the next state will be 0 1. So, that means, if your input is 0 1, I will go to state 0 1, next state will be 0 1. Similarly, if it is 0 0 and if R1 is 1, automatically G1 will be 1, and if R2 is 0, this will be 0. So, if I am in state 0 0, if my input is 1 0, I will go to state 1 0, right. Similarly, if it is 0 0, R1 and R2 is 1 1, R1 is 1, that means G1 is 1, and R2 is 1, G1 is 0, R1 is 0. So, this will be 0 because R1 is 1. So, not of R1 will be 0. So, that means, even if I am in 0 state, if my input is 1 1, I will go to state 0. So, I can write do not care because 1 0 and 1 1. So, this input does not matter. So, I will just write 1 x, I will go to this. So, similarly, I have to consider 0 1 state and there will be 4 combinations, right. Then 1 0 state there will be 4 combinations, 1 1 state there will be 4 combinations of R1 and 2, and every time I will calculate the next state based on these equations and I will complete this FSM, right. And so, this is what I obtained here. So, this is my complete FSM, right. So, the start state is, let us say I am assuming that by default G2 is 1. So, this is my start state and this will be my exact state transitions. So, I will strongly recommend you to complete this table and you will effectively get this FSM. You should cross check that. Okay. So, one thing you can note here, this both G1 G2 is 1 1 does means both the signals are 1, right. So, this is kind of mutual exclusive property violation, right. Ideally, you should not reach this state ever, right. So, that is what is happening. If you are starting from 0 0 1, you see there is no transition coming here, from here only transition is going there. So, it means at least mutual exclusion property is getting satisfied here, right. So, I am not reaching to this state starting from the start state. But why I am putting this state here? Because you may start with this state. So, by default you are say G1 equal to 0 and G2 0 and next state the value will be what. So, based on that I just complete this FSM. Okay. So, the first part is done. So, we, as you mentioned, the first part is effectively the FSM extraction and the next part is model checking. So, what is model checking? Model checking, you basically have this FSM now and you have this property. You will take one property and you try to identify the path in which path this is getting satisfied, right. So, this can be done using simple depth first search or breadth first search kind of algorithm. We will talk about those algorithm explicitly in subsequent classes, but I will give you kind of the notion today how model checking works. Okay. So, this FSM extraction is done. So, given a design you identify what are the state variable and then what are the inputs, and you have to check for each state variable for each input possible value what will be my next state, right. So, this is how we will construct, okay, and there is no shortcut there, you have to do this. Now, for model checking, as I mentioned that it try to identify a path in the FSM. Now, ideally this model checking algorithm, what it does, it basically take the negation of the property, okay. So, what effectively does, model checking algorithm searches all possible path in the state machine that refutes one of the property. So, why it takes the next, so what effectively if your property is say phi, it will take negation of phi, okay, and it try to find a path in which this not phi. So, this is the path say pi, and they try to identify pi satisfy the not phi. Why I am doing this? Because if I found a path, that will be my counter example, right. So, that is why you take the negation of the formula, not the original formula, because if you start with this phi and you say you found a path pi that satisfy phi, it just say that there is one path, right, but you have to identify all paths, you have to identify all path in which this gets satisfied. So, you have to find pi 1, pi 2, pi 3, pi 4, you do not know how many paths are there. So, first of all you do not know how many paths you have to identify, there may be many paths, and also only you can say oh this property is satisfied when you identify all paths. But the advantage of taking negation of the path, if you just identify one path in which pi satisfy, you do not have to find the next path, because this path satisfy the negation of the formula means this path does not satisfy the original formula. So, this is the counter example, right. You just say that this is the path which violates your original path. So, so this is what the advantage of taking the negation of the formula, right. So, what effectively model checking algorithm does, it basically take the negation of the formula and try to see the path that actually satisfy the negation of the formula, which means it refutes the original property, okay. So, if such path exists, it report this is the counter example, and if it cannot identify any such path, it says that means the original formula satisfy in all paths, right. So, this is what the advantage, right. So, you just try to identify one path that satisfy the negation of the formula. If that exists, that means that is the counter example on which the original formula does not satisfy, and if no such path exists, that means the original formula satisfied by all path of the implementation, right. So, this is what the model checking algorithm. Now, let us take any of the property, let us say this property, and I have to check whether this implementation satisfy this. So, as I mentioned, you have to check all paths starting from the start state, because this is from your starting, right, you do not need to search for other paths. So, one important point here, you know that you do not have any end state. If you remember your finite state machine, the regular automata, if you remember those things, we usually define that with the end state, because this is where it terminates. But in hardware, it always running, right. Ideally, hardware never stops until you stop it forcefully. So, that is why this FSM does not have any end state. Every state there are some next state. So, if you come to this state, you will go to the next state if some input comes, right. So, to stop the hardware, you have to stop giving input, right. So, that is the path that I was talking about here. These paths are infinite in nature. So, the path is basically of infinite length, it is not of finite length, okay. So, now let us see this example. Let us say I have taken this formula P1, okay. What is saying that if R1 holds in a state, in the next 2 cycle G1 should hold. You have to identify a path where it is not happening. You see, so suppose let me give the state name is S0, this is say S1, then S2 and S3, okay. So, now there are many paths here, right. You think about a path which is basically path 1, which is S0, S0, S0. So, it basically rotates here. So, this is one path where your, so this G1 is equal to 0, G2 equal to 0, and this is basically R1 equal to 0, R2 equal to 0. So, R1 does not come. So, this path is not important to me, because R1 is not true. So, if it is false, by default this property is true. If there is implication P implies Q, if this is 0, by default this is vacuously true. So, in this path, this S0, 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 in this path R1 is always 0. So, I do not need to check that. You think about this path. In this path also you have 0, 0, right. So, I do not need to bother about. So, you think about pi 1, which is say S0 to S1, you come to S1 and then you say probably take say this S2, right, S2. So, I am taking out this path now, right, and then you think about is happening here. So, I have S0, S1, S2, 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 it will repeat here. Okay. So, now this path which has this. So, now you think about here R1 is 0, no problem, but R1 is 1 here. So, whenever R1 is 1 in the next state G1 is 1. So, that means it is happening here and R1 is 1 again here and it is repeat here. So, G1 remain 1. So, next state and next state G1 is true. So, I can say pi 1 satisfy this the property P1, right. Sorry, this is pi 2. So, pi 1 also satisfy, pi 2 also satisfy P1. Now, think about this path. Okay, let me just remove this. So, let me take the next path, which is say this is S0, S1, S2, S3. Let me I take this path, this and it is rotate here, right. So, this is the infinite path. So, pi 3, which is S0, S1, S2, S1, S2, S1 and this will repeat. Now, you see here you have R1 equal to 1, next state G1 is fine, but it says that next state also G1 should be true, but I am coming here and G1 is false here. So, this path is not satisfying this property, right. So, that means pi 3 does not satisfy P1, right. So, I am just saying here with the original property, but ideally it should check the negation of the property. So, effectively what I am saying that I found a path which is this. In this path the original property is getting violated. So, that means this implementation is wrong, because in this implementation there is one execution path in which property 1 is not satisfied. So, there is bug in the implementation, and which if you now look back, it is obvious, because what I am doing here, I am just doing G1 equal to R1. I am not thinking about what will be the next cycle, right. I am not keeping track of that. I am just bothering about the only the next cycle. So, I am ensuring in this implementation that G1 will be true whenever R1 is true in the next cycle, but I am not ensuring it will be true for next 2 cycles, right, and that we identify here, right. Now, you think about take any property, let us say P2, right, which is basically say if not G1 then G2. So, that means if G1 equal to 0 and G2 must be 1, right. So, that means G1 equal to 0 means G2 must be 1, then only this will be true, right. So, this is the state 0 1 state, right. So, this is the 0 1 state. So, what is, so if you think about this state, so you are saying that you cannot reach a state where this is not true. So, if G1 equal to 0, G2 must be 1. So, it means you should not reach a state 0 0 from 0 1. So, your initial state is satisfying this, but if you take a path this, right, you take any path like say pi 4, which is say S0 then S1 to S0 S1, so it is repeating like this, right. This is the path. In this path I am going to this state which is not satisfying this property, right. Again pi 4 does not satisfy P2, because I found a path here, I go to this state 0 0, but the requirement is that if G1 equal to 0, G2 must be 1. It means the 0 0 state should not be reachable from the start state, but it is happening here, right. So, again I found a counter example that violates property 2. So, this way if you take any property, let us say I take P3 now, P3 saying that at least one of them should be 0, right. Both of them cannot be 1. ideally, right. So, now it means you cannot have a state 1 1 which is reachable from the start state, and which is happening here, right. If you see closely, this I have already discussed earlier also. If you think about this diagram, so the state which is both one is this, right, S3. So, I am basically saying that whatever the paths are there, that path should not reach S3 starting from the start state S0. And you see here there is no incoming edge to this state, right, all is outgoing edge. So, I can say that whatever the paths are there from S0, so that will never reach this state. So, I will say this implementation, this model, right. So, I will say model M satisfy P3, right, because I mean I am just giving intuition here, because this state is not reachable from this state. So, whatever the path you say, this may be one path, this may be one path, right, this may be one path, this may be one path, right, you come here and rotate here, this may be one path, you come and rotate here, you come from here and rotate here. So, there are so many paths, right, so many traces, every traces you never have reaching the state 1 1. So, I can definitely say that this model satisfy at least property 3. Okay. So, this way you take one property and you can check this. I am just trying to show what model checking algorithm does internally, right, but we will definitely show you the precise algorithm how to do this. Okay. So, I hope you understand what is this overall model checking algorithm, but I will talk about the scalability of this model checking algorithm. And this is one of the well known problem which is called state explosion problem. What happened? You have to extract the FSM from the state machine, and in my example there are 2 bits. So, number of state possible is 2 to the power 2, which is 4. But we now think about the design has 30 state bit. So, the number of state possible is 2 to the power 30, which is exponential, right. So, the number of state is exp of number of state bit, and that is problematic, right. So, you always get an exponential size FSM. So, the model checking algorithms are very efficient, they are polynomial time to check whether there is a path on which the property holds or not, or the negation of the property satisfy or not, right. So, that algorithm is simply by DFS or BFS, those kind of algorithm. So, this is efficient B plus E kind of algorithm, right, which is polynomial time. But the problem is the size of the machine itself is exponential. So, even if your algorithm is polynomial time, it is basically exponential, because you are working on a exponential size state machine, and that is one of the biggest problem with the this model checking. So, the questions naturally come, do we need to extract this FSM, right. So, can we model check without explicit extraction of the FSM, because our objective is to find out whether there is a path in which the negation of the property holds, right. So, can I do this without extracting the FSM, and the answer is yes. Okay. So, it is possible to do that, and this is what we will discuss at the latter part of the course. So, we can actually model the state machine as a BDD, and we can actually do this path searching as just a BDD operation, right. I have already talked about BDD in this course, binary decision diagram, specifically ROBDD. So, we will show that effectively you are doing a search, finding a path, right. You are in this state, you want to go to the next state, from this state I can go to the next state, something like this, right. So, these things can be possible by constructing an ROBDD of the implementation without constructing the FSM, right. Similarly, I will also show that it is also possible to do this model checking, which is nothing but searching a path from the current state, what are the next state, from this state, what are the next state. So, this kind of things can also be done when I encode the entire state machine as SAT formula, and whether the path exists or not, I can just check by the satisfiability of that formula. Okay. So, these are the 2 most important innovation in the model checking thing which make this model checking practical. With these 2 technology, model checking actually avoids this scalability problem, and it can handle large design. Still there may be, because you already know that BDD also have the state explosion problem, that you do not know what will be the variable order under which this BDD will be smaller size. Similarly, the SAT formula will see if the depth of the formula is long, SAT formula will be too big, and then SAT can also have the memory issues, but nothing even if that without these two, model checking cannot be used in practical sense by extracting the FSM, right. So, the most important thing we will discuss in this course, how do you basically encode this model checking problem as a BDT state transition problem, or how do you encode this model checking problem as a satisfactory checking problem. So, these are the two things we will cover in the course at the latter part of this. So, with this I conclude today's class. Thank you.